let's get started. Today we'll continue on, finish up not too many slides on central limit theorem, but I'll also show you some MATLAB as it pertains to central limit theorem. And then we will spend probably most of the class period talking about the project. I have not posted it yet. In fact, I just finished up these slides on the project after my first class this morning. Things get pretty hectic at the end of the year, plus also the overload. But anyways, so why don't we just continue. So we left off where we left off. There we go, turn this on last time. Oh, yes. Oh, so that's what happens when you get in 4.5 hours of sleep. Administrator. So today is the last day of classes, which you're all aware of. Tomorrow is reading day, also PMAX day. I encourage all of you again, especially if you are in the market for a capstone project, I encourage you to come to PMAX day, which is tomorrow, the 6th. I don't know for Somni, did he send out a schedule? You did? Okay. I didn't see it, so I haven't checked my Slack or my email. But nonetheless, it's always a fun time, especially interesting time, especially if you're in the market for a capstone project. So our scheduled final exam period is on the 10th, which is Tuesday. So this coming Tuesday from 10:30 to 12:30. And during that time, you'll be giving project presentations. I will push out the project for this class and my operating systems class right after this, between now and when I have my 4:30 graduate class that I teach also. So I will push that out, but I will talk in detail about what that project will involve. You will have some leeway to choose a domain and to design a model yourself, and hope you have fun with it. It will require you to think, to analyze, to observe, and to design, and you'll be implementing this in MATLAB. I wouldn't expect you to do this in Java or Python. It's much easier in MATLAB. And so on the 10th, between 10:30 and 12:30, you'll be given project presentations, and it'll be on what your project is about and anything else you want to say about it, where you are, if you have made a lot of progress on it, and so forth. And it's your opportunity to get feedback and also share with your class, your colleagues rather, what you're doing, as well as get some experience in presenting, which is very important. And then the final project will be due when the residence halls close on Friday the 13th, not so scary, at 8 p.m. And please put this in your smartphone to buzz and ding and make all sorts of noises to you that it is due at 8 p.m. and not 11:59 and 59 seconds, right? Every semester, there's always one person. Please don't be that person who says, oh my gosh, I thought it was a second before midnight. So write it on a Post-it, put it on your fridge, put it in your smartphone, do whatever you need to do to remind yourself that it's at 8 p.m. Okay. Any questions? All right, so let's continue. Where we left off last time, we talked about the central limit theorem, and we talked about this idea that you can have a random variable, so some observation, and it can be governed by any distribution, one of the distributions that we talked about, like the Poisson, the gamma, the geometric, the exponential, the binomial, the Bernoulli, the negative binomial, all sorts of that good stuff, whether continuous or discrete. And these distributions behave differently. And we said that if you transform them suitably, and that transformation involves a sum, if that sum has enough components, right, then it doesn't matter what distribution it is, it will look like a normal distribution. And the central limit theorem is that theory that proves that this is the case. And why you care about it is sometimes you want to compare stochasticity of one type of system to another system. So let's say you have something that looks like the interview problem, and the stochastic variable of interest is the number of people you interview in order to find a suitable candidate. And you want to compare that against something like a binomial, like the ice cream problem. You're asking yes/no question. Each yes is governed by a probability, and you want to know the probability that you ask n people that some number k of them are going to say yes, right? And so those two are different, And in order to compare maybe the mean and the variance and so forth for those two different systems, they need to be the same distribution, but if they're different, how do you get there? Well, you get there by computing some transformation on the samples from each of those systems. And that transformation, if it involves a sum, and you sum together enough components for some definition of enough, then you get both of them looking like normal distribution. And then as we had discussed before, if you normalize that normal distribution, you subtract from each value the mean, and you divide by the standard deviation, then they become a standard normal, and you can make some very easy comparisons about what the outliers look like, what various mean and standard deviation, various statistics look like, and make fair comparisons. Okay? All right, so one example is the average, right? So suppose you have some observation, like the number of people you interview, and you have another observation, for example, the ice cream problem, and you want to take the average over a number of samples. In the case of interview, that's the number of people you interview. In the case of ice cream, it's the number of people who say yes. If you take those samples a bunch of times from those distributions and you average them, you can now compare them because they both look like numbers. And so one of the, continuing on this, first, any questions about this? Any questions? Okay, so this kind of completes our tools in our toolbox. We talked about a bunch of distributions. We talked about what stochasticity is. We've modeled a bunch of things. And now we can compare models even though they have different distributions. You first cast them as normal distributions, and then you standardize them, and now you can make fair comparisons, even though they're different systems. So let's choose a random variable, and let's take a look at what this sum looks like if we compute the summary statistics for it. So let's say you have some sum, Sn. And Sn, just like the slide before, is just a notation to say you're going to take n measurements or observations and you're going to sum them together. So x1 would be the first observation, x2 would be the second observation, x3 would be the third observation, and so forth. And you have little n many of these observations, you're summing them together and you're calling it Sn. So that n in the Sn represents the number of observations n that you're summing together, right? It's just notation. So if we were going to take the variance of this sum, right, and what we'll do is take the variance and we take the expectation of it, and then we look at another transformation and show that it does behave like a distribution, right? The quantity, which is the result of summing. So if we take the variance of the sum, right, we said the variance of the sum is the same as the sum of the variance, and we learned that earlier in the semester when we talked about the linearity property for the variance. And so that means n times we're going to take the variance of the individual variables because Sn is just the sum of n many of these variables. And so here we write generally x sub I, where I can be 1 if it's the x1, and I can be n if it's x sub n. So that's just notation of saying the ith sample. Okay, so we have the variance of the sum is the same as the sum of the variances, so n many times we're going to take the variance of the ith item, and the variance is sigma squared, so that result is n times sigma squared. Likewise for the mean, as we had learned earlier in the semester, has a linearity property. The expectation of a sum is the same as the sum of the expectations, so we have n times the expectation of the ith sample, so n times expectation of x sub I. You have n many terms, each one is the expectation of the ith sample. So it's n times expectation of x sub I. Expectation of x sub I is just mu. That's the Greek letter that we substitute for expectation, so we get n times mu. Now, of course, if you have a lot of terms in your sum, as n gets really big, approaches infinity, for this result, for the statistic, i.e. S sub n, this sum, we have the variance of the resulting thing is infinite, so the variance is unbounded, so it's not really behaving like a distribution, and the expectation is also unbounded. So that doesn't help us very much. But what happens then if instead of the sum, we take an average, right? And when you take an average, what you're doing is you're dividing the sum, each of these x sub i's by n. So you sum them up, and many of them, the first sample, second sample, third sample, and so forth, and then you divide by n. In similar fashion, you can call that the same as multiplying each one of these terms, x1, x2, x3, up through xn, multiplying each of these terms by 1 upon n, right? That's the same as dividing the sum by n. It's the same operation, right? So let's assume that we're going to now take the average. We're going to take the sum, right, which we just showed the mean and the variance as the number of terms increases. It's unbounded, it's infinite. Let's now take this sum and divide it by n, right? We're going to multiply by a scalar 1 over n. So what happens there? Well, let's now look at the expression for the variance of the statistic, the average, right? And let's look at the expectation and see how that changes. So if we take the variance of this average, which is nothing more than the sum divided by n, now anytime you multiply by a scalar, we learned earlier in the semester, the variance changes by that scalar squared, right? And so we write variance of Sn over n is just the variance of Sn over n squared, right? And of course that squaring comes from the fact that in the definition of variance, you're going to have x minus mu quantity squared. And that's where that squaring of the constant comes from. And so here we write variance of S sub n over n squared. And so if we do this, well, variance again has a linearity property. So we have n times sigma squared, which is what the result was that we had from before in the numerator. And then we have our n squared in the denominator. So we have a copy of n in the numerator and the denominator. A 1 cancels with the other, goes to 1, and we're left with sigma squared over n. Likewise, for the expectation, if we were going to take the expectation of this average here, Sn over n, again, expectation exhibits the linearity property, right? And so expectation of Sn, so we have our n comes out of the expectation. That's 1 over n times the expectation of Sn. And we just got done on the previous slide saying that expectation of a sum is the same as the sum of the expectations. We have n many terms, so it's n times the expectation of each sample xi, right? So we end up with a copy of n in the numerator, n times the expectation of xi, and n in the denominator. So we can cancel the n in the numerator with the n in the denominator, and we're left with just mu. So now, simply by taking the average, we look at the variance of the average, the statistic of this function, and the expectation of the average. And as n approaches infinity, we see that the expectation, it's mu, it's finite, right? It acts like a distribution, it has a finite mean, and the variance goes to 0, right? Because as n goes to infinity, that denominator underneath sigma squared gets really big, and some fixed quantity over something really big is 0, okay? Or approaches 0 in the limit. Any questions about this? Does that make sense? So what does this mean? It means that if you have a sample, it doesn't matter what distribution that sample comes from. If you compute the average, or you have a sum in some transformation, along with multiplying by a scalar, right? That result acts like another distribution, and that is a true distribution because it has a finite variance and a finite mean. So what does this mean? Well, let's also take a look at what that variance says. If your samples get really, really, really big, that variance goes to 0, right? And we'll actually see that play out in some examples in MATLAB. So the variance goes to 0, and the expectation is finite. It behaves like a proper distribution. And moreover, because of something called the law of large numbers, this distribution has a form, and its form is the normal distribution. Okay? All right. Any questions about this? No? Does that make sense? So this is the central limit theorem. What it says is that when it behaves like a distribution, if the number of samples in this transformation sum and multiply by a scalar, if the number of samples is big enough, it acts like a normal distribution that has a well-defined variance and a well-defined expectation. And that's the central limit theorem. Okay? And you can use this to convert any distribution to a normal, and once you have two distributions converted to a normal distribution, you can now make fair comparisons between the two. All right, so it behaves like a distribution, and often this is called convergence in distribution, right? When you have a large number of things, it behaves like something else. a convergence in distribution. And so here, let's see, why do I take the square root? Okay, yeah. So instead of taking the average, if we change that scalar from 1 over n to 1 over square root of n, we take a look at what happens to the mean and the variance, right? That's just to show you it's not just average, it's multiplied by scalar. Take the sum and multiply by a scalar. So we're going to change that scalar to 1 over square root of n. So if we take our sum, s sub n, and we divide it by square root of n, and we take the variance and the mean of that, well, let's see what happens with the variance. Well, the variance of a scalar is the scalar squared times the variance of that set of variables. So we square radical n, we get n in the denominator, and we have the variance of the sum in the numerator. By linearity property for the variance, we get n times sigma squared in the numerator, and n in the denominator. The n's cancel, go to 1, and we're left with sigma squared, right? So just by choosing that scalar appropriately, right, the variance of that transformed version of from one distribution looks like a normal distribution with variance sigma squared. And likewise, the expectation, if we take that sum and we multiply by scalar 1 over radical n, we have linearity of expectation again. So we have n times the expectation of x sub I in the numerator. We have radical n as the denominator. And another way of saying n is radical n times radical n. One copy cancels with the denominator, and we have radical n times mu, right? Again, we have a finite expectation. So in the first case, we had mu, our expectation. In the second case, we changed the scalar from 1 over n to 1 over radical n, and we have the variance of the resulting transformed distribution is sigma squared. Okay. Any questions about this? No? All right. Does that make sense? So it behaves like a distribution, and in fact, it behaves like a standard normal distribution. And we will take a look at this. As a normal distribution, right, you have some mean and some variance. And now, as a normal distribution, you can take this transformed distribution that now looks like a funky normal through some transformation, and now you can normalize it. So what do? You take this sum, right, or sum times a scalar, you subtract off its mean from each measurement, and then you divide by the square root of the variance, right, which is the standard deviation. And that transforms it from that funky normal distribution to now a standard normal distribution. And then you make your comparisons between the two systems using the standard normal. Okay? Any questions about this? Does that make sense? And so this normalization is just like the normalization we talked about before, only you're normalizing the result of a transformation, not the raw distribution you sampled from. Okay? Questions? No? All right. So, why is it such a big deal? The reason why the central limit theorem is such a big deal is that it doesn't matter what your distribution's form is. You use a distribution to describe examples that you sample from some system. And it doesn't matter what that distribution is, right? It doesn't matter what the form of that stochasticity is. As long as you have a large enough set of observations, you can perform a transformation on it, sum and multiply by a scalar, and make it a normal distribution. And then once you normalize, now you can make comparisons. So the central limit theorem gives us this mechanism that we can use to compare the variability and the form of two different systems, even if they were governed by different distributions. It's a really powerful mechanism. Does that make sense? Any questions? Okay, so that's how we make a single method to compare things, even though at the end of the day, they started out differently. Bless you. All right. No questions? No? All right. So let's take a look at this for real before we get into the project, right? Let's kind of end the show momentarily. I hear movie action scene music. Oh, I was gonna start MATLAB and have an exciting MATLAB session, but all right. So here we have a MATLAB session, and I've already, written it and I'll just explain what these things are. So I use a bunch of sampling routines from MATLAB, and you can look them up. Here's Poisson R&D. That's for sampling from a Poisson distribution, and I assume a lambda of 6. I just made it up, right? And so here, with Poisson R&D, you give it the parameters of the distribution. So Poisson is indexed or has a parameter called lambda, which is the rate. And then you give it a shape, and it says fill a 1 by num samples array, which is a vector, and num samples equals 10,000 in this case. Fill a 1 by 1,000 matrix or vector with samples from a Poisson, assuming a lambda of 6. And so it'll give me 1,000 samples from this Poisson. And so then what I do is I create a figure, and then I compute a histogram of those Poisson samples. So that says, assuming a rate of 6 per window of observations, delta t, sample. And so it's simulating 10,000 times the observation of events in windows of time. And then I compute a histogram with 20 bins, so nummed bins is 20, and that's going to show me the number of counts of all of those numbers of events observed for that Poisson arrived upon by sampling, right? 10,000 samples. So the shape is going to be the shape of a Poisson distribution. So I do that for a Poisson. I also do that for a binomial distribution. Again, a binomial, you have a probability of success is p, right? And here p is 0.3 or 30%. And binomial tries 1,000 times. I'm going to sample given a probability of success of 3. Given some number of trials, binomial trials, which is 1,000, given a probability of success of 3, I'm going to see how many successes I have out of 1,000 trials. And I do that 10,000 times. So 10,000 many times, I'm going to say, if I flip a coin with probability 3 of heads, if I flip that coin 1,000 times, how many successes am I going to have? So it's going to simulate that number of successes out of 1,000 flips, assuming a probability of heads of 30%. So I do that 10,000 times, and then I compute a histogram to show you what the binomial distribution looks like. I do the same thing with the geometric distribution. The geometric distribution, we talked about the interview problem, right? You have a probability of hiring. In this case, success is 25%, 0.25. And so for the geometric distribution, saying assuming the probability of success is 25%, brain fart. What is the number of interviews that I'm going to make before I actually hire someone and get a success, if the probability of success is 25%? And so it's going to tell me how many times did I interview people for a job, and I'm going to do that for num samples times. So that's like saying for 10,000 different jobs that I'm advertising, right? What is the number of people that I interviewed? And that's the geometric. I take that, I plot a histogram to visualize the distribution. I do the same thing with a uniform distribution, and that's a continuous distribution on the real number line. A and B are 1 and 100 respectively, and I say uniform at random, give me a number, if they're equiprobable between 1 and 100 on the real number line, give me 10,000 samples uniformly from that, okay? And then I compute a histogram. So I do the same thing also with the exponential distribution, given a lambda of 10, the rate parameter. What's the amount of time between the occurrence of the next event, right, between events? And so it's going to tell me, here's a time between events, here's a time between events. I do that 10,000 times, and I plot the histogram to show you what the distribution is. So I do that also for the gamma. Gamma is that multi-stage execution. I have alpha many steps. In this case, alpha is 5, and the rate lambda is 10, right? I'm sorry, yes, the rate is 10. So what this says is that give me the amount of time it takes, given that the rate is 10, governing the exponential distribution, describing the time for each step in that 5-step process. Give me the time for this end-to-end computation, right? So I do that 10,000 times and plot the histogram for the gamma. And likewise, for the normal distribution, I have my mean and my variance, standard deviation. And of course, when you talk about the parameters of the normal distribution, it's the mean and the variance sigma squared. But in MATLAB's API, when you call the sampling routine, you give it sigma, which is the square root of the variance. So One is mathematical, and this use in MATLAB, that's just how they happen to implement their API. Why they did it that way, I have no idea. I would have said mu and sigma squared if I were implementing the API, but I didn't. So you have to use what they implement. So anyways, I say, give me a sample governed by this normal distribution, and I get 10,000 of such samples and plot the histogram. Okay, so that's just the straight visualization of the distributions for the normal, for the gamma, for the exponential, for the uniform, for the geometric, for the binomial, for the Poisson. So it's a lot of distributions we've studied, right? So let's run this and take a look at what those histograms look like. So we do that, and that's pretty quick, 10,000 samples, right? It's pretty efficient. And if we look here, let me blow this up, and we see that's the Poisson, right? And one of the things you'll notice with the Poisson distribution is that the smaller that lambda is, the more skewed to one side, to the left side, that this hump will be. It'll be kind of mushed over to one side. It'll be lopsided. And as lambda gets bigger, that hump is going to move more and more and more and more to the right. And that's how a Poisson distribution behaves. And that's why the lambda parameter is often called the shape parameter as it pertains to the Poisson distribution, because as you turn down or turn up lambda, the shape of this distribution changes to come from left skewed to right skewed. Likewise, if we have that second distribution here, that's the binomial, right? The binomial distribution, it's typically symmetric, because it talks about the binomial sum. And it kind of looks almost even, it's not quite even. And if you change this p value, right, it's going to make it kind of more shrunken in or more dispersed out. So it's like almost like a scale parameter. So then if we look at the geometric, right, here's our geometric. If we take this lambda, it's going to change the shape, and it's that hump is going to shift from the left over to the right. And if you look at the uniform, it's almost straight across, right? That's what uniform looks like. Now, it's not perfect, but as you increase the number of samples, it gets more and more and more close to being straight across, equal probability. Then we have the exponential distribution. It also has a shape parameter. So the hump is over here, and then the gamma. It also has a shape parameter, because at the end of the day, the gamma is just a bunch of exponentials, one after the other, trafficking in time. So all those shapes together kind of have a bigger hump, if you will, and that hump will move from the left to the right as you change the alpha and the lambda. Then you also have the normal. It has a location scale parameter. Mu is location. As you change mu, this symmetric hump will shift to the left or shift to the right. As you change sigma, it'll flatten down and kind of get more dispersed, more spread out, right? So here we have these distributions, and they absolutely look different from one another, right? Especially something like the uniform and the Poisson and the exponential and the geometric, right? Okay. Any questions about this? Make sense? So now what we'll do, that's just the plain vanilla distribution. So now we'll continue on with the execution of our computation, and now we'll take advantage of the central limit theorem. So what we'll do now for the Poisson, we're going to sample 100 times from the Poisson and then compute the mean of those 100 samples, and we're going to do that some large number of times, num trials, right? And so here, num samples is 1,000. So we're going to sample from this Poisson 1,000 times, take the average of that 1,000, mean of Poisson RND, num samples, right? And then I'm going to save all those means, because a mean is nothing more than a sum times 1 over n, right? And I'm going to save all those means, and then I'm going to plot the histogram of those means and show you that the histogram of those means looks normal, right? And what we'll do this for all the different distributions, the same ones that we showed before, and show you how now they all look like normals. They look more like one another, okay? Now certainly, you have to do this enough times because how the central limit theorem works is as the number of samples in the sum increases, it looks more and more normal, right? Okay, so let's do that. So let me just continue here, and we do that plotting of the mean for the Poisson here. We do that for the binomial here, right? So here we have num trials. We're taking the mean of 1,000 samples from the binomial, and then we save those means, and then we plot the histogram of the means, right? And we do that for all these same distributions. So let me just continue and get to the point. It takes a little bit because now I'm doing samples instead of just values. There we go. So there's the second figure. So let me make this a little bit bigger. And if I had it as 400, it would look exactly like a normal. But that's going to take a little long. You just have to trust me on it. I can post the code and let you try it on your own. But this is the Poisson, right? And if we compare the Poisson, average of Poissons, to the regular Poisson, you notice here the regular Poisson is more skewed to one side, but this the average of Poissons is much more symmetric. And if I bumped up the number of times I computed the average from 100 to 400, you'd actually see it get very, very smooth. Let me see if I can do that. If it takes too long, I'm just going to cut early and get right to the stuff about the project. So here, num trials, I'm going to make that 500, right? So 500 times, I'm going to take 1,000 samples and compute a mean. So I'm going to have 500 means for each one of these distributions. Okay, so let me run that. That was the original. And let me continue. And hopefully it doesn't take too long. Chug, 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 chug. If it takes more than like another 30 seconds to a minute, I might punt on this. So as you can imagine, 500 times you're going to take a sample of 1,000 things, right? And then take an average. So that's 500 times 1,000 and taking averages. That takes a lot of computation. So as I continue to stall here, you can hear the fan on my CPU starting to wake up a little bit. And we'll see. There we go. That wasn't too bad. All right, so now you can see it much more dramatically here, right? So this graph, figure 2, is the graph we have using the mean. So here we sampled 1,000 times from a Poisson. We took the average of those 1,000 samples and we did that 500 times and then we plotted. So that's figure 2. Where did figure 1 go hiding? So here's figure 1, right? So figure 1, we see the Poisson, and we see, I wonder why there's that gap there. I wonder if it's a graphics artifact or, well, anyways. So here we have the original Poisson. You notice it's skewed. Now, taking advantage of the central limit theorem, it's symmetric and looks more like a normal distribution. And moreover, you'll notice each of these, even though they're from a different distribution, they kind of look more like a normal, more like one another. And if we did the normalization procedure, they would look exactly like one another because we're shrinking down to a variance of 1 and we're centering it about origin. Okay? Now, one of the things you'll see here, this exponential, that becomes what's called a point distribution, and the gamma is a point distribution, and the normal is a point distribution. That is an artifact of exactly what we talked about in this slide when we talked about what the variance looks like when you take an average. As n goes to a really large number, the variance goes to 0, meaning that you have all the probability mass on one value. There is a 0 variance. It's called a point mass, right? And that's what's happening with the exponential and the gamma, because if you think about it, for this simulation, the original samples weren't that different from one another, so as you take an average, the variance kind of trims down really, really quickly for the amount of samples that I've taken, which was 1,000 when I took the average. Okay? Any questions about this? So this is just to show you that the central limit theorem is a real thing. It's an important tool that allows you to take any distribution samples, cast it as normal, and then you normalize that result, and then now you can make comparisons between the stochasticity of two systems, even if they were different from one another. Okay? Any questions? Does that make sense? I will certainly, after this, also post this code for you to tinker with it and play with it yourselves. Okay. It's not magic, it's just central limit theorem. Okay. Questions? No? All right. So let's get rid of MATLAB, and let me check the time. It is 12:39, so we're here to 1:15, so we're making good time. All right, let's continue on from there. All right, so Please be cognizant of the key dates. Again, that most important one, well, they're both important, the presentation. It's going to be about 5 or 7 minutes. I'll put that spec in the assignment PDF when I post it. But please be aware both of the presentation time during the scheduled exam period and also be cognizant of the final due date. It is at 8 p.m. and not 11:15 p.m. Not 11:50. It's at 8 a.m. and not 11:59 seconds p.m. No, I just did it again. 4 hours and a half hours of sleep. It's at 8 p.m. on the 13th of Friday the 13th, and not at 11:59 and 59 seconds p.m. There we go, the third time. All right, so please make sure you are aware of these dates. All right, so let's talk about the final project. So your task, and I will update the slides. I just finished these slides about 20 minutes. No, that was caffeine. About 40 minutes after my first class was over. You'll be choosing an establishment, your choice, and this establishment must have, you'll be doing some analysis on this establishment. That means you'll be analyzing a process that you view at the establishment, and you'll be collecting data. Now you don't have to sit there with a stopwatch and a video camera, just kind of rough estimate. And don't be weird about it. Because if you all go to Target and that's your establishment and they see you all with cameras and stopwatches looking at their processes, you're gonna invite some scrutiny that is not healthy for you, right? So don't be weird about it, right? And don't say, oh, Holmes told us not to be obvious. Don't hide behind a pillar and start looking like that. Because they're not gonna take kindly to that, right? And then don't say, certainly, well, my professor told me to do this, right? You can choose something on campus. If you choose something off campus, just use good judgment, right? So you're going to collect a little bit of data. It doesn't have to be super precise. Just use your best judgment. And then you can develop a model. Now, the attributes for this establishment, you have to have customers that arrive. And, you know, the word customer, you can be loose about what customer means, but you still have to have people who need something from this establishment that arrive in time. You also, once they arrive, there's going to be a multi-stage execution because the thing that they need requires a multi-stage execution. So those two, bless you, are requirements. And then the other requirement is that you have to include customer attrition, meaning that if it's going to take too long, they leave at some probability. So they stay or they leave when they see it. And that's, you know, typical, right? You go into the subway on campus and you go at the wrong time of day and say, oh no, right? You see like 20 people in line out the door and say, you know what, I'm gonna go, right? You go to Chick-fil-A and so forth. So choose an establishment. It must have customers that arrive. You're gonna do some analysis. It has to have multi-stage execution, and it's up to you to decide what those stages are from what you observe the process to be, right? So, you know, think about it and be reasonable. It doesn't have to be 100 steps. Heavens no, but it has to have some number of steps. And then you have to study it. And so you can already see where this is going, right? You're gonna use different distributions to model different aspects, and then you're gonna sample from them, right? And the outputs of one sample is gonna impact what you do with another sample, right? And then also the attrition, you're gonna be using that to decide if the output from one sample is gonna be used for the input from another sample, okay? All right, any questions about this? So it should be fun, right? Have fun with it, be creative, and I expect there are going to be many variations for this, but these are the requirements. Okay. So here's an example. You know, I drive to Massachusetts a lot. You know, that's where I'm from, and you know, a lot of family there. And I like to go on the Jersey Turnpike. I like New Jersey rest stops. They seem to work really well, better than Massachusetts rest stops. Certainly the one rest stop in Delaware is okay, but I like the New Jersey ones. And one of the things in rest stops that people think about is the bathroom experience, right? Sometimes there's a line. So I'm gonna just kind of go over some high-level ideas about the bathroom problem at the New Jersey rest stops. Now, this is just an abstraction. You don't have to say, oh, there's a family bathroom, Dr. Holmes. Yes, I know that, but let's just assume simple, right? So what is a restroom? Okay, so you have a line, people that are waiting. You have a men's room, you have a women's bathroom, and in each bathroom, you have a bunch of sinks, and the sinks are, yeah, that's the only GIF I could find. It's, yeah, they're happy to wait in line. So you have the women's bathroom, men's bathroom, and in each restroom you have some sinks, and those are the S's, blue for water, and then you have green because green is a good contrast on the slide. You have toilet stalls. Now, I know that there are urinals. Yes, I know, but just simplify. Imagine there are toilet stalls. So you have 3 stalls in the women's, or some number of stalls, and 3 stalls in the men's. You have 3 sink units in the men's and 3 sink units in the women. And the idea is that one person uses a toilet, and then he or she then goes to a sink, right? That's not the case in reality, but this, in the simulation, imagine that is the case. So what happens here? Well, let's say someone arrives at the bathroom. Well, you're going to use a Poisson distribution to model this. And so think about the observation that you would make. The number of events that occur in some unit time is going to influence the rate that you use. That's the observation that you're going to make. And so you're going to do this for some amount of time, right? You're going to record some data, and you look at how people arrive. And when they arrive, they go in. Now, don't be creepy and sit there and across from the bathroom and watch people go into the bathroom, right? Just, use your good judgment, okay? All right. So you're going to use a Poisson distribution. You're going to observe an actual bathroom, right, from the outside. And then you're going to determine what the rate should be. And then you're going to model this in MATLAB. You're going to sample from a Poisson distribution. And that's going to give you, for each unit of time delta t, the number of people in simulation that arrived at the bathroom. So you're given, let's say you sampled and you said 3. 3 people gave back. Number 3, 3 people arrived at the bathroom in some delta t. It doesn't matter what delta t is. It could be 5 minutes, 2 minutes, could be half an hour. Let's just be reasonable. I don't expect you to sit there in front of a bathroom for an hour, right? So use your good judgment. So then, once you sample and say return 3, each of those 3 people is going to do something. What do they do in the case of the bathroom? And you can't use the bathroom. That's this. Again, you can't say, oh, darn it, wholeness took bathroom. I took bathroom because I didn't want to use an actual establishment to make that off limits. So, anyways, you can't use bathroom. So once each of these 3 arrives at some period of time in the bathroom, each person, then there's an attrition. If they get to the bathroom, and the bathroom is currently being used, all the stalls, right? Then this person's going to wait in line, these people. Now, as people wait in line, of course, new people will arrive in the next delta t, and more people will arrive, and more people will arrive, and you'll have a number of people that additively is waiting for the line in the bathroom. So, of course, for every new person that arrives, they look at the line and decide with some probability, I'm not going to wait. I'm going to just forget about it. I'm not going to get in line. I'm just going to go someplace else. And you're going to model that attrition, right? And the probability of attrition is going to be directly proportional to the number of people that are currently waiting. The larger the line, or number of people waiting, the higher that probability will be. But you still have to simulate that attrition. It's either wait or not wait. Okay? Any questions? Okay. So, the longer the line, the higher the attrition, and you're going to choose a distribution. I mean, 2-way outcome, probability of success, you all know that by now. And then you're going to implement that in MATLAB. So if first you arrive from the previous slide, and 3 people arrive, then for each of those 3, you're going to do that attrition and decide if each of those 3 that arrive is going to join the line or going to leave the line and just not go. Okay? Any questions about this? Make sense? Okay. So once you go through the attrition process, for those that are using the service, then you have the usage. And of course, when you use a bathroom, thought about what happens when someone uses a bathroom, and you come up with a bunch of steps. These are just steps I made up, right? You enter the stall, right, getting ready to use the bathroom. You defrock, you prepare whatever clothing needs to be prepared or undone, whatever, to use the bathroom. You physically use the toilet. You then clean up. You redress yourself. I don't know if refrock is an actual word, so I just call it dress. Then you flush the toilet, and if it's automatic flush, just assume that it takes some time to flush the toilet, right? Keep it simple. and then you exit the stall, you wash your hands, right? So this is a multi-stage execution. And as a multi-stage execution, there's a rate associated and there's an alpha describing the number of steps. It's up to you in the process you observe to determine what those steps are and associate a rate with it through observation. Does that make sense? Any questions about this? So for each of those that doesn't walk away due to attrition, when they use the resource, they're going to go through a multi-stage execution, and you're going to simulate for those that are waiting in line. And use a gamma distribution to do this, and you're going to model it in MATLAB, okay? By sampling from the gamma. Okay, so now, of course, if you add the fact that someone buys something, put in a step that the last phase in this multi-phase execution is going to be the payment, right? And you can just assume once this multi-phase execution is done, you can either say after it's done, there's some money involved. You can assume if you want to, you don't have to, that everything costs the same. Or you can assume that you have a bunch of stuff at different costs and they randomly select something uniformly. Okay? It's up to you. So the last step is paying, and you can either have pay as the last step in this multi-step execution, or pay is just something that happens after this multi-step execution is done. It's your choice. Does that make sense? Any questions? And so what it is, you're taking different simulations and using the outcome of one piece of the simulation to influence what happens with the other piece of the simulation. Now, you could choose with time. In MATLAB, there's a pause function, and that pause will actually stop execution for a certain amount of time and then continue. You could use something like that as the way you simulate something taking time. Or you could just say, okay, when I sample time, I have this idea of a clock, and I keep adding that time to the clock and use that as the mechanism for saying, I'm looking at the clock and it's advancing with some number. You don't have to say like, is it 5 o'clock or 5 p.m.? Just have a number that just increases as the wall clock. Does that make sense? All right, any questions about this? Okay, so please, it's more of a design. The individual pieces, both the arrival, the attrition, and the multi-stage execution, at the end, the pay is just adding that dollar value to a register that increases. And so the question that you're going to answer is, of course, how much money is made over time. And that's going to change based on the parameters. If you're modeling an actual enterprise, now then the question is, what do you need to do to improve things? Now, of course, with this bathroom problem, if the line gets long, I would increase the number of toilet stalls. But you know what? Real estate being what it is, you can't just add on more building, right? So what I would do is I would make this wall movable so that you have a unit toilet stall, and then you can take this wall, unplug it, kind of roll it forward, and then move it like there and replug it in and kind of change how many toilets are each one. And I made them adjacent with the toilet stalls on purpose. So that's what I would do. So you'd have a whole bank of toilet stalls. Maybe you have 4 here, or 8 here, and 8 here, or whatever, and just make this wall movable. So now the women's room has more stalls, or the men's room can have more stalls, right? So that way you can increase the number of resources if you find that one line is waiting too long, right? Or if you're at an establishment, maybe you open more registers. There's some stores that you never see the registers not open. But nonetheless, I'm looking for your unique recommendation, and this is the important part, based on the numbers that you get from simulation about what you would do to improve something, right? Because there's going to be something that you'll find that goes wrong. Okay? Any questions? Does that make sense? No questions? None? So I will include the central limit theorem right after this. I'll post it, and it also serves a secondary purpose to give you an example of sampling from the various distributions. Okay? All right. So with that, I will end there. And this is what modeling really is. And the difference is in the complexity of the model, how many moving parts you have. Because you can imagine you could have more than one multi-stage process for a model for something. And you have all these interconnections. Now, this is a simple one, right? You have the arrival, you have the attrition, and then you have the usage of the resources, right? Which is in a multi-stage execution, and then you pay at the end. But you can imagine if you make different decisions, based on the decision you make, you can choose from more than one different multi-stage execution, right? So imagine that, you're going into a spa, or maybe, you're getting work done on your car. Depending on what you choose, it could take a different amount of time, and that multi-stage execution will be different depending on what you select. So we're not doing that, we're just doing one thread through a process, but the ideas are very similar when you have a lot more moving parts, and moreover, you could also have cyclic behavior implemented. So let's say, you're going through Target and people actually do this. A lot of times those overhead cameras, they're not just for loss prevention, they're also to see what happens in terms of the dynamics of an organization. If you instrument your system, you notice that for certain establishments, their rate at which people come in, it might change. So let's say you have 12 hours of operation from 6 a.m. to 6 p.m. And maybe you divide the day up into 1 hour units of time. And each hour you divide up into 10-minute chunks. So your delta T represents 10 minutes. And based on a lot of samples, you have one Poisson describing the arrival time for the first hour of operations, another Poisson for the second hour, another Poisson for the third hour, and so forth. So you have 12 different Poissons, each with its own lambda that you're setting based on observation of people walking through the doorway over time. And you can do that completely automated, like we saw with that overhead camera, counting customers entering the store, going through the entry box of the store, right? So that's absolutely something analytics-wise you can do, and people really do use that to do things like how many employees should we have on staff at different times of the day, right? Because there's certain rushes of customers in the evening, in the morning, and then even if you have that 12 Poisson model for the arrival time for each of the 12 hours of operation, you could certainly make that now seasonal, right? When it's back to school shopping time, that's a different time of year. When it's Christmas holiday shopping season, that's a different time of year. When it's the spring, thaw, so to speak, that's a different time of year. So not only can you have that 12 Poisson model representing 12 hours, each of the 12 hours of operation, you can also have a different 12 for each season of the year, or various milestones that might be important for your business, right? So people really do this, and they pay a lot of money for folks to analyze this, because if you think about it, if you just kind of naively choose the number of employees that you have on staff, well, they say, oh, well, we need 10, right? All of a sudden you have 10 employees, and maybe they're not doing much, and you're losing a lot of money because the amount of revenue you're generating can't support all those salaries. Okay? So have fun with it. This is just a single kind of thread. You have the arrival, the attrition, and the use of the resource as a multi-stage execution. Use actual observations and design of an enterprise that you like, use, see, whatever, to build your model and have fun with it. Okay? Any questions about this? No questions? Does that make sense? Yeah? All right. So I'll get to writing this up, and I'll post it right after this. And I thank you. Well, it was required, of course, but still, I try really hard, as much as possible, to make this stuff accessible, enjoyable, fun. It really is an exciting discipline to be in. It's a lot easier than software engineering, because software engineering, 5 years from now, you're going to be learning something else. Math, you learn math once, and you know it, right? It doesn't change for generations. So I really hope, don't believe me, look on the job boards. There's tons and tons and tons of modeling, analysts, quants, all that sort of stuff, jobs out there. And you only need to learn it once and you're set for your career. So I really hope you consider it. It gets particularly exciting when you talk about sensors and trying to use it to describe stuff from sensors and applications that make their own decisions. I had fun. It was a great class. I hope you had fun. You learned something. And I'll see you all next semester. Okay. And that is it. So we'll end there. And I'll look forward to your presentations